Hello all. In this lecture, we will continue the discussion of Green's function. Actually, now we are going to determine the Green's function or construct the Green's function. In the last lecture, we have already seen that we have defined the Green's function as a function which must satisfy the some special properties. That means actually it is a function where we defined like the kernel, isn't it? And we have formulated the integral equation of the corresponding differential equation using the Green's function. We have seen that the Green's function must be of the form g of x theta must be which has the value g1 which has a function of x g1 of x when x is less than theta and it is equal to, it must be equal to g2 of x when x is greater than theta, and also it must satisfy the four properties, that is it must satisfy the equation, the homogeneous differential equation Ly equal to 0. And the second condition G must satisfy is that it will satisfy the homogeneous condition at the endpoints. That means G1 must satisfy the homogeneous boundary condition at x equal to A, and G2 must satisfy the condition at x equal to B. And the third condition, third property was G must be continuous at x equal to theta, and the fourth condition was the derivative, about the derivative. That means the derivative is discontinuous at x equal to theta and has a magnitude of discontinuity minus 1. Minus 1 by p of theta, where p of theta is the coefficient function of y double dash. That means we have the equation Ly plus phi of x, the second order equation in this form. Ly plus phi of x is equal to 0. And Ly plus phi of x is equal to 0. Where L is the differential operator, which is given by p into d square by dx square plus p dash d by dx plus q. Now the corresponding homogeneous differential equation is of the form Ly equal to 0. So Ly equal to 0 is a linear second order differential homogeneous differential equation. Therefore, here we will discuss the construction of Green's function. So in order to construct a function g which has a split function which is equal to g1 of x for x less than theta and g2 of x for x greater than theta, we will consider the first of all we will consider the corresponding the homogeneous equation Ly equal to 0, and let u of x be a non-trivial solution of the this second order homogeneous differential equation Ly equal to 0. And this satisfies, that is y equal to u of x also satisfies the prescribed homogeneous condition at x equal to a, and let y equal to b of x be a non-trivial solution of Ly equal to 0 which satisfies the condition at x equal to b. So for finding the Green's function g in the form of in the form of a split function g1 and g2 which also satisfy the four properties, of which 1 and 2, the conditions 1 and 2 are first one, it should satisfy the equation. It should be a solution of the equation, homogeneous equation Ly equal to 0. That means so it is when we take g1 of x as u of x, then the first condition is satisfied. When x is less than theta, it is equal to u of x, g1 of x is equal to u of x, and g1 it satisfies the g1 satisfies the prescribed homogeneous condition at x equal to a, which is the second property for Green's function. And when y equal to v of x, when we take v of x as g2, we also see that properties or conditions 1 and 2 are satisfied. So we can choose a multiple of u of x can also be the solution. So generally we will take g1 of x as c1 into u of x and g2 of x as c2 into v of x, where C1 and C2 are any constants. So we can see that the conditions 1 and 2 are satisfied. That is when g of x theta is defined as C1 into u of x when x is less than theta, C2 into v of x when x is greater than theta. We can see that when x is less than theta, or g1 of x is c1 into u of x, this u of x satisfies the equation Ly equal to 0 and also satisfies the condition, homogeneous condition at x equal to a, and for g2 we can see that it also satisfies the the equation, homogeneous equation Ly equal to 0 when x is greater than theta, and also it satisfies the boundary condition at x, homogeneous condition at x equal to b. So the conditions for 1 and 2 are satisfied. Now in order to get the condition 3, what was the condition 3? Condition 3 is g is continuous at x equal to theta. So for condition 3, we have this must satisfy the condition C1 at u of theta, C1 is C1 at u of theta, sorry, C1 at C1 into u of theta must be equal to C2 into v of theta, or we can write it as C2 v of theta, uh, C2 v of theta minus C1 into u at theta must be equal to 0. And for condition 4, it is for the derivative, that is g dash at x theta is or dou g by dou x. G dash is not does not exist, so we can write it as dou g by dou x is equal to, for a fixed value theta, dou g by dou x is equal to c1 into u1 dash of x and c2 into c1 into u dash of x and c2 into v dash of x. And we have the condition 4 is that the discontinuity is g2 dash at theta minus g1 dash at theta. The magnitude of discontinuity is minus 1 by p of theta. So this implies, for this it must satisfy C2 into V dash of theta minus C1 into U dash of theta is equal to minus 1 by P of theta. So, so this must be satisfied, or we can C1 and C2 can be determined from these equations. So for solving C1 and C2, let the equation be numbered. The conditions 3 and 4 to be satisfied can be numbered as 4 and 5, or this can be written in matrix form also. For that, we are rewriting the equation. Equation 4 can be written as C1 into U of theta minus C2 V of theta equal to 0, and C1 U dash theta. And the second equation is equation number 5 is C2 into V dash theta minus C1 U dash theta is equal to minus 1 by P of theta, which can also be written in the form C1 into U dash theta minus C2 into V dash theta is equal to 1 by P of theta. So writing this equation in the matrix form Ax equal to B, we have the matrix A as U theta, U dash theta, first column, second column minus V of theta minus V dash theta into matrix C1, C2 is equal to the matrix 0, 1 by P of theta, where P is the leading coefficient of y double dash in the equation Ly plus phi of x equal to 0. So this has now the equation is in the form Ax. X is the unknowns to be determined, that is the matrix C1 C2, column matrix C1 C2. Ax is equal to B. So this system of equations has a unique solution if and only if determinant of A is non-zero. Now what is determinant of A? Determinant of A is determinant U of theta minus V dash minus V of theta, U dash theta minus V dash theta. Since there is minus 1 in the second column, we can take it outside. So this will be is equal to det of A is equal to minus of U theta V theta U dash theta V dash theta, determinant of this. Now determinant of A is non-zero if and only if this determinant is non-zero. Okay, so we can say that this equation, system of equation has a unique solution if and only if the determinant U of theta, V of theta, U dash theta, V dash theta is not equal to 0, or this determinant is the actually the Wronskian of the two non-trivial solutions U of x and V of x of the homogeneous second order differential equation Ly equal to 0. That means this system Ax equal to B has a unique solution, or we will get the unknowns C1 and C2. We will get unique values for C1 and C2 if and only if the Wronskian UV dash minus U dash V does not vanish or not equal to 0. And the Wronskian is this becomes 0 only if they are linearly dependent. U and V, which are the two non-trivial solutions of the differential equation Ly equal to 0. So if they are linearly independent, then the Wronskian is not equal to 0. And if the Wronskian not equal to 0, then determinant of A will be minus of Wronskian of UV. So determinant of A not equal to 0. Hence we will get unique values for C1 and C2. Now, before finding the values for C1 and C2, first of all, we have to use an identity that is known as Abel's identity. So to get the value U of theta V dash theta minus U dash into V of theta, or to find the Wronskian of the two solutions, it is given by the Abel's identity or Abel's formula. And so let's discuss that first. Then we can find the values or determine C1 and C2 if the W, if the Wronskian exists, and then thus we will get the function, Green's function. Okay, for that, first we will move to prove the Abel's formula. The statement is if u of x and v of x are two non-trivial solutions of the differential equation Ly equal to 0, then Ly means actually we have given the equation in the bracket. If Ly equal to 0, then P into u v dash minus u dash v. U v dash minus u dash v is actually the Wronskian W. So we have the formula as P into Wronskian equal to A, or Wronskian W is equal to, we can write it as A by P. What is P? P is a function, P is the leading coefficient of what? Y double dash. P is the leading coefficient of Y double dash. So this is the Abel's identity. Now we have to prove this. This is a very important identity. This is frequently asked for university exams. State and prove Abel's identity. So please note this identity and study this. Okay, since u of x and v of x are solution, so we have to prove that Wronskian is equal to a by p, or p into w is equal to a. This we have to prove. And given that u of x and v of x are two non-trivial solutions of the second order differential equation Ly equal to 0, homogeneous differential equation. So it satisfies u of x and v of x satisfies the equation. By that we will get the two equations 1 and 2, that is instead of y we can substitute u, and also for v. So for u we have the equation number 1, and for v we have equation number 2. Now in order to eliminate this, sorry, here it is not p, this is q. QV is equal to 0. So in order to find the relation, we will multiply equation number 2 by u and equation number 1 by v, and eliminate the third term by subtracting. So we have u into the second equation, p v double dash plus p dash v dash, and the third term will get cancelled, minus first equation we multiplied with v. So minus v into p u double dash plus p dash u dash equal to 0. Now combining the p terms together, so p into u v double dash minus u double dash into v, plus p dash into u v dash minus u dash into v equal to 0, and we know u v dash minus u dash v, this we have to determine. Okay, so once again, if we consider this first term, the term in the first, the factor in the first term, that is u v double dash minus u double dash v, this is the actually this function is the derivative of u v dash minus u dash v. That is solved here. That is, when we take the derivative of the term u v dash minus u dash v, we will get there is, in the first term there is a product u into v dash. So first when we take the derivative, first function into derivative of the second function is v dash, so its derivative will be v double dash plus u dash v dash minus of then u dash into v dash minus u double dash v dash, then u dash v dash and minus u dash v dash get cancelled, then we will get u v double dash minus u double dash v, which is the factor in the first term. So this can be considered, equation number 3 can be rewritten as p into u v dash minus u dash v derivative plus p dash into u v dash minus u dash v equal to 0. So the equation, if we call the u v dash minus u dash v as another variable, if we call this by another function, that is, let it be some m, then we have p into m dash plus p dash into m equal to 0, like this. So this is also a chain product rule of differentiation. So this we can write it as d by dx of p into m. Actually this is the expanded form of this one. So we have p into u v dash minus u dash v whole derivative is equal to 0. Integrating this with respect to x, we will get the required result. We obtain p into u v dash minus u dash v equal to a, where a is any constant. So this is the required identity. Okay, so now we obtained what is u v dash minus u dash v. So when we know what is this one, so u v dash minus u dash v, so Wronskian, this we have obtained as p by, sorry, a by P. Since all these factors and theta, we can write it as P A by P of theta. Now, if a W Wronskian is equal to this one, then determinant of the matrix A, determinant of the matrix A, the delta, we denote it by delta, is equal to minus determinant U of theta, V of theta, U dash theta, V dash theta. So, this is equal to minus A by P of theta. So this is the determinant delta. So we can solve for C1 and C2 by any of the methods you have studied for finding the solution. So here since A is non-zero, that means determinant is non-zero, we will get the unique solution, and that can be found by any of the rules. So first here we will discuss the Cramer's rule. That means finding the determinants, finding the unknowns using determinants. So the determinant of the matrix A is minus A by P of theta, which is denoted by delta. And in the Cramer's rule, our solution is given by, that means the unknown solution of the values of the unknowns are obtained as C1 will be delta 1 by delta. What is delta 1? Delta 1 means in the matrix A, in the determinant of the matrix A, we will change the first column with the matrix B. We will change, or we will take, instead of the first column in A, we will put the matrix B, and if in order to find C2, the second unknown function, second unknown, we will C2 is using Cramer's rule. C2 is equal to delta 2 by delta. Now what is the delta 2? It is the determinant obtained when the second column of the matrix A is replaced with the B. Okay, so using that relation, using that formula, Cramer's rule, we have obtained delta as minus of A, minus A by P of theta, and delta 1. You can see that instead of U of theta, U dash theta, that is the first column of the matrix determinant A, we replaced it with the matrix B. What is the matrix B? Matrix B is 0, 1 by P of theta. You may not consider this as, the equation can also be written in some other form also. Then there will be some minus sign, but I have converted the equation so that C1 comes in the first position, C2 is in the second position. That is C1 and C2 are the matrix. X is the matrix C1, C2. First column, first element is C1. Say first column, second element is C2. Or this can also be written in the form in which X comes in the form C2, C1. So in that matrix, B will be minus 1 by P of theta, but here it is 1 by P of theta. So delta 1, we replace the first column by the matrix B, 0, 1 by P of theta. Then multiplying this, we will get the delta 1 as V of theta by P of theta. And delta 2, replace the second column with the B. So we will obtain the delta 2 determinant as U of theta by P of theta. Now we have C1 by Cramer's rule. The first unknown is equal to delta 1 by delta. Here the first unknown is C1. So C1 will be V of theta by P of theta, that is delta 1 by delta. Delta is minus A by P of theta. So this will become minus V of theta by A. And C2 we will obtain in the same way as minus U of theta by A. Now we have already defined the Green's function as C1 into U of X. and when x is less than zeta, when x is greater than zeta, Green's function is C2 into V of x. So now substituting the values of C1 and C2 here, we will obtain the Green's function as minus 1 by a u of x into v of theta when x is less than a, and minus 1 by a v of x into u of theta when x is greater than theta. That is g of x theta is equal to minus 1 by a u of x into v of theta whenever x is less than theta, and minus 1 by a v of x into u of theta when x is greater than theta, isn't it? Where a is a constant that can be determined by Abel's formula, that is P into W, the Wronskian W is equal to A. So instead of A, we can apply this also. Then we can find the Green's function. So we have formulated, or we have constructed the Green's function g of x theta in terms of the non-trivial solutions of the equation Ly equal to 0. So actually our second order differential equation was Ly plus phi of x equal to 0, the non-homogeneous equation. So the corresponding if we once get the Green's function, then we have already proved that y of x is equal to integral 0 to L g of x theta phi theta d theta, d the corresponding integral equation. Okay. Sorry, not 0 to L. Whatever be the interval given, that is we took it as general a to b, integral a to b. So this will represent the corresponding integral equation whenever, and we now so in this lecture we have already constructed, or we have determined how to find the Green's function using the non-trivial solutions u of x and v of x of the corresponding homogeneous differential equation Ly equal to 0. And once we get the Green's function, the corresponding integral equation will be in this form: integral a to b, y of x equal to integral a to b g of x theta phi theta d theta. If the function phi is given as a direct function of x, then this equation will get this gives the solution of the given differential equation. Otherwise, this will represent the corresponding integral equation. Okay, so let's stop here. We can continue, or we can discuss the further how to find the solution of the differential equation using Green's function and all other things in next lecture. Thank you all.